continue, I want to introduce some more about the spin. Let's know about the physics of the spin. What is a spin? Again, you don't need to ask the details. It's just like you never ask why the electron is negative charge, while the proton is positive charge. Spin is just like the charge. It's an extra characteristic of an electron. And in the past, no one see it until maybe Pauli or someone found that says something called spin. And they say, hey, you know, electron has a characteristic of spin half or negative half. Right? Just an additional characteristic. Of course, you can have a lot of philosophical discussion. Maybe people even can relate this to why there is new universe. They do have all these complicated equations, right? But that is spin, just an additional property for the elementary particle. So if that is the case, then you agree for an electron or proton, its spin S is either plus or minus half. That's it. It is given. Okay, just like we tell you the charge is either plus or negative or zero. There are three possible values. I mean, not three possible. I mean, the fundamental particle, maybe many values, but yeah, okay. Like the quark or whatever, right? So every spin, but why do we call it spin? You need to know that it's just characteristic. It's not talking about the electron is spinning. Electron is a point charge. It cannot spin. A point cannot spin because you cannot distinguish whether a point is spinning or not spinning because it's a point, right? But however, somehow it gives something called angular momentum. Spin angular momentum, which is equals to the spin times h bar. That's it, right? This is the Planck constant. The reason it is called spin because looks like it is spinning. It does have an angular momentum. Okay? Now, if you have an angular momentum, right, then what happened? Because you have a charge, just from classical physics, you might forgot already, I forgot also. I just let you know if a charge has an angular momentum, you are going to have something called magnetic moment. Okay? And this magnetic moment, mu, equals to G E divided by 2m times your angular momentum. Okay? Then it's getting more and more stuff, right? But the point is, remember about this, right? The magnetic moment is equals to the angular momentum times something called the gyromagnetic ratio. In this case, it's G times E divided by 2m. This gyromagnetic ratio is that gamma because G actually is very close to 0.02 or something. I forgot the last digit. G is just a constant. Yeah. It's very close to 2. So this gamma is very close to E over m. Okay, and so that's it, right? So I just want to let you know two things. The G of electron, actually I have the number here, equals to negative 2.0023. It is negative, right? And then the G of a proton is 5.586. This is positive. Okay, so here is the main point. I say all this, you basically don't need that, right? Unless you want to calculate the magnetic moment. Here is the main point I want to tell you. Now, if I have a positive charge, for example, proton, if the spin, if it is spinning up, what is the direction of the magnetic moment of the proton? Based on this equation. If the spin is spinning up, it means the angular momentum is up. You have the same direction, right? Because the G is positive. Then I have the magnetic moment pointing at the same direction. But what if it is an electron? If it is spinning up, right? We say the electron is spinning up. Where is at the magnetic moment? Pointing down. Very good. Because it has a negative G or a negative gyromagnetic ratio. Yeah.
Is it okay in some energy they call protons holes?
Photon?
Holes.
Call what holes?
Hole. And proton.
We don't call, proton is not holes.
Okay. I don't know if like they usually produce their electron.
But holes is the lack of electron, right? So we don't call it, electron and proton doesn't have a direct correlation. Yeah. Yeah. Okay, but anyway, this is the main point I want you to memorize, because this is going to change how you view the broad sphere in the future. You need to be careful whether they are using a negative charge as the spin or positive charge as the spin. If it's negative, then the spin and the magnetic moment are in the opposite direction. So what is a big deal, right? That is because if you have a spin, you have magnetic moment. Then if you put it in the magnetic field, a moment in an external field is going to generate the energy. Okay? So you will get the Hamiltonian equals to negative mu dot B. Okay, so if you have a spin, you don't have magnetic field, no one can find out whether you are spinning up or down. But once you have the magnetic field, then the energy of the system will change. Okay, so let's look at this carefully. If I have a magnetic field pointing up, right, and I have the magnetic moment pointing down, what is the value of this H? They are in the opposite direction, right? And let's think about what is the meaning of dot product again. Is the magnitude times the magnitude times cosine theta, right? The angle between them. When they're pointing in different direction, cosine theta is what? Theta is what? 180 degree, right? Pi, yeah, pi, right? So cosine theta is -1. So if they're pointing in opposite direction, you actually will have a positive energy, right? So your system's energy will increase. On the other hand, if the magnetic field is pointing up, the magnetic moment also point up, then the Hamiltonian is going to be less than 0. And Hamiltonian is the total energy of your system, right? So due to this magnetic field, you actually lower the energy of the system. You're supposed to be more stable. Okay? Now, let's look at two examples. Then what does it mean? For if it is a proton, for example, positive charge, I have the magnetic field pointing up. I definitely see in this case, I also have the spin pointing down, right? Because the spin and the magnetic moment are in the same direction. This is the case for the proton. Right? So when the spin is pointing down, then I have this case. So when the proton spin and the magnetic field are in opposite direction, you actually get higher energy for the system. But for electron, when the magnetic field is pointing up, the magnetic moment is pointing down, it means actually the electron has a spin pointing up. Right? Because when electron spin is pointing up, then the magnetic moment is pointing down, right? So if the electron and the magnetic field are in the same direction, you actually get higher energy. So it's opposite to the proton case. And similarly, for the proton, when the magnetic field is pointing up, your magnetic moment is pointing up, it means you will spin up. This one gives you a lower energy. But for electron, when your magnetic field is pointing up, magnetic moment point up, it means the spin is pointing down. This one gives you a lower energy, right? So if you want to achieve a lower energy for the system for electron, you need to make the spin in the opposite direction of the magnetic field, right? It is confusing, so you don't need to write it down, but just be careful. The equation is negative of magnetic moment dot the magnetic field. That's the first thing. And then the spin is opposite to the magnetic moment if it is electron. And then use this, just trace it carefully. Okay? Now then, we don't care about proton in this class. We only care about electron, right? So for the electron case, what does it mean? Now, if I try to draw a diagram, this is the energy scale from low to high. If the electron is spin up or spin down, when there is no magnetic field, they have the same energy. Here it's trying to say the energy is the same, whether it's spin up or spin down, right? What happens if it is spin down? What happens if I have a magnetic field? I should say I have a magnetic field that is pointing up, right? That is pointing up. Then you will see that there will be a splitting of the energy that you usually see. For the spin is pointing down, look at this. Spin is pointing down. It means magnetic moment is pointing up, so energy is smaller. You actually have an energy splitting that you reduce the energy by mu. I will just give the total value, right? By mu B. Your system reduced by mu B. But if you have the spin, which is pointing up, then you actually gain more energy, right? You increase the energy of the system by mu B0. Okay? Oh, and I forgot to emphasize, what is this mu? This mu just equal to E divided by M, right? Oh, that's it. Not E divided by M. The mu, I forgot to write this careful here first. So what is the mu if this is like this one, right? So I say that, let me look at this term. And I try to borrow this space. This is approximately equal to E divided by M. And what is S again? Is H bar divided by 2. Correct? So the energy is approximately E H bar divided by 2M. Right? So you're splitting. Why am I missing an H bar there? G is about 2, cancel with the 2. G and 2 are cancelled, and then S is H bar divided by 2. Yeah. Somehow my notes doesn't have the bar, but I think I just miss it. So this is approximately equal to E divided by 2M H bar times B. This is E H bar 2. This is M, right? I just try to spell it out. That is what I want to say, right? We'll use this later. But basically, what is the total energy difference now? It's EH bar divided by m times B, because each of them is divided by 2. And you add them together. That is EH bar B0 divided by m. Okay, maybe a little bit messy, right? But the important thing is the spin will change the total energy of your system. Whether it's spin up or spin down, it will determine whether your system will increase or decrease. But for electron, if you go in the opposite direction of the magnetic field, you actually have lower energy. Same direction, you have a higher energy. And total energy difference is EH bar divided by m times B naught. Each of them is further divided by 2. You add them together, this from this level to this level, right, is EH bar divided by m B naught. Okay? Okay, so we spent some time to understand the system. If you are interested, of course, you can spend the whole semester just to understand all this fundamental physics, right? But this you just treat as given, and you trust the physicists, what they told us, right? So now, if I have the electron in the magnetic field, of course, yes, I do have the Hamiltonian, but this is just telling me what the energy it is, right? But how do I construct the matrix of the Hamiltonian? Then let's think about the physics. When you do a measurement, you measure an electron spin. In a magnetic field. Right? You try to measure it. How do you measure? You actually need to do some energy measurement. See if you can excite a state, whether you can absorb the photon or whether you will release the photon, then you know whether it's spin up or spin down, right? You will get the energy E equals to B mu positive if it is spin up, right? I assume, here I assume the B is pointing up, right? So if it's spin up, they're pointing in the same direction, I get higher energy because the magnetic moment is opposite, right? Or you just check this, when it is spin up, when it's spin up, same direction as the B, I get higher energy, correct? And, or you will get negative B mu if it is pointing down, right? So that is the, our observable, right? This is what we know. Now, so in order to construct this, then I need to look at the basis. Our basis, whether we are going to use spin up, step, spin down as the basis, we can say, how about I call this spin up? I give you a name. Let me just call it the excited state because it has energy, right? For bracket notation, I call it any name. You can put it English, Chinese, Japanese, and everything inside the bracket location. And I'm going to call this 0. Now, this is a confusing, right? Because sometimes we think 0 is lower state, but it really doesn't matter. Just call it 0, which is the excited state in this case. For spin down, this is the ground state. I call it 1, okay? So because of this, then the Hamiltonian is going to be the eigenvalue times the outer product of its basis state, right? So here I measure either this value or this value. These are the eigenvalue of the operator corresponding to this Hamiltonian, right? Because remember we say all the measurement, right, all the operator corresponding to a measurement is Hermitian. Remember that slide? It's Hermitian, and the eigenvalue are real. And when you do the measurement, you will get one of those eigenvalue depending on the probability, depending on the square of the coefficient of that state, right? So the eigenvalue of zero, zero, right? Or now I call it spin up, give me this one, right? And the other eigenvalue is minus, because I just show you that this is negative when it is spin down. When it is spin down. How do I construct the matrix? If I just let the first one as the first basis, so the first basis is the excited state. The second one as the second basis. Again, this is just a name. I will get something like this, right? And this one, I'm going to factorize it out now. This is just equal to what? What is 0, the first state? It is, thank you, 1, 0. Because it's the first state. And then minus what is 1, 1? 0, 1, 0, 1, right? And this one will give us, the first one give us, let me just jump, 1, 0, 0, 0. Yeah, the second one give us 0, 0, 0, 1, right? So with this, I know that the result is B mu times 1, 0, 0, negative 1, which is sigma C. Okay, so again, it confirms our understanding. The Pauli matrix sigma C corresponds to the operation when we measure the energy of a spin when the magnetic field is in the Z direction, right? So by doing this, I constructed the what do I call? I constructed the matrix for the Hamiltonian of this system. Right? We construct it because we know what are the possible measurement outcome. You can get this from experiment, right? Just one thing. So just let you know, in general, right? I just had this. In general, if you want to construct a matrix for the observable, it is equals to summation I equal to 0. Right? In this case, it is 1. Maybe I also say 1, you only have 2 states. You just take the eigenvalue times the outer product of this, right? Now, whether this is correct, of course, some of you can see it. If not, we can do a quick check. We can do a quick check. For example, what is the eigenvalue of this when this matrix is applied to the spin up? B mu, this is the whole matrix, right? Apply this matrix, this operator matrix, to spin up. What do you get? Well, it is B mu 1, 0, 0, negative 1. Spin up is what? 1, 0, right? What is this? It's still equal to B mu times 1, 0, right? Because 1 times this is 1 and this is 0, right? So I do show you that indeed this is the eigenvalue of this matrix, and this is the eigenvector of this matrix, right? Just a checking. So play with this back and forth. Is this okay?
So
yeah.
Would you, suppose you ask us a question like this, would you give us the values from B and mu?
If I don't give you, you just use whatever I give you, right? Just a symbol. Or you say this is an eigenvalue. Then you use this equation, the eigenvalue will be in front.
Okay.
Yeah. So, I kind of forgot what I want to say here. Yeah. So in this case, I have an external magnetic field in the 3D space pointing up. And now I'm talking about electron, not proton. So is this state, the top, what is that? Right? So this one is actually the spin up because it has higher energy, right? So it's up to you, right? You just need to be careful. I don't think it's necessary to say the top one is the excited state, but sometimes, usually we want to do that, right? So in this case, this is the spin up state, and it is also the excited state. This is the spin down, and this is the ground state, right? But if yours is a proton, then it will be opposite. The bottom one is going to be the ground state. The top one is the excited state. Okay? It doesn't need to have the higher energy on the top, right? Because its Box field will just embed into our 3D space, okay? So it's difficult to memorize. The point is just I want you to be careful about this. Otherwise, you will get confusing. And many people, when they discuss, they don't really distinguish. Usually, you don't need to distinguish which one is higher or lower. Okay? Now, so